Okay. All right. So today I will talk about some of the news from the current observing ground that is still ongoing, and I can just quickly say that I did my PhD at Embry-Riddle University in Arizona, and before I was here, I did a bachelor and master in this department, in this chair of gravity. And after my PhD, I went to Florida, where I did my postdoc, and now I'm here working in this department again. And a very quick announcement for students: in a year from now, not this semester, but the following semester, like after the next summer, I will have a one-year course on gravitational waves. So spreading the news gently so people know. This just a month ago, we had a celebration, the 10th year celebration of gravitational wave astronomy. So GW 150914 was the very first gravitational wave that we have ever detected. And some flashbacks. When I was starting my PhD, I had a pleasure to be at the very beginning of this beginning of gravitational wave astronomy. And even before that, I joined the LIGO-Virgo-KAGRA collaboration, at the time just LIGO-Virgo. And we had, for example, Kip Thorne coming for these meetings. And I have like, when you have like pop stars, you always like ask for the signatures. And here I was asking Kip Thorne, like, hey, can you like give a signature on my like conference tag? And he said like, yeah, please find gravitational wave for me in March 14, 2015. And then just like a few months later, we had the discovery of a gravitational wave. So I was like, yeah, yes, sir, mission accomplished. And just as some like souvenirs, I have a science magazine about gravitational wave detectors from 1992. So like long history. The original announcement in physical review letters about the discovery, and the very latest 10th year anniversary of gravitational wave in the LIGO magazine. So if anybody wants to see, and anybody just to break ice to come and talk to me after the presentation, here it is. And I'll just like also add that in the astronomical department, we had at the celebration of the 10th year anniversary, we have a beautiful cake for this anniversary. And this is the Polish group working on gravitational wave astronomy. Here I am, and then Alejandro Casalas Lagos, who is a postdoc with me, and who is sick, he couldn't be here in the department. But yeah, this is the group, the Polish group that is working on gravitational waves. So coming back to business, the fourth observing ground. I'll talk about the introduction, some about gravitational waves that we have detected, and what's next. We got 10 years of the detections. What can be happening in the next 10 years? Then I will talk about core collapse supernova. This is a source of gravitational waves that someday we hope to detect, and I will talk about that. I'll talk about what happened here in Warsaw at our department during the summer, some lessons learned, and then I will give a summary. So let me start from the fourth observing ground by a very swift introduction to gravitational wave astronomy. So how to generate gravitational waves? In order to generate gravitational waves, we need to have some spherical asymmetry. If you have a star that is rotating, even super fast, it does not emit gravitational waves. However, if you introduce like a small mountains, like even a millimeter size mountain on that star, so for example pulsar, then you have continuous emission of gravitational waves. So the more bigger asymmetry, the bigger generation of gravitational waves, and this is called also like a quadrupole emission. And the most efficient emitters of gravitational waves are compact binaries, so binaries made of black holes or neutron stars, but also some other sources like cosmic strings, also like on the more exotic side, like cosmic strings, primordial black holes, some mass events, and collapse supernovae. Later, I will elaborate more on the gravitational waves that we have detected and what we can detect soon in the future. Then, how do we detect gravitational waves? First of all, we are using gravitational wave interferometry. Gravitational waves, when they pass through our detector, they basically modify the distances, and we measure the difference between these two distances. Basically, we have a laser source that is hitting our beam splitter. Then the light is split into both arms, and then it bounces back to the beam splitter from both directions, and then recombine in the photodetector. And the detector.
Selmek i Ciunali.
Okay, just interact. Okay, so when it recombines in the photodetector, when the two arms are tuned to have destructive interference, then our photodetector, basically there is no light inside. But when the gravitational wave is passing, the difference in both arms creates different in phase, making showing light in the photodetector. So the longer gravitational wave detectors, the more sensitive we are. We are basically measuring this difference that is proportional to the length of the detectors and to the strain that we are measuring. So this is the real view of the LIGO detector in Hanford, northwest of the United States. And then for half a year, I was actually a fellow over there, and I was one of the few people actually who were allowed to go inside like big chambers where you have these lasers. This lens suspended. They are basically of this size. You have in order to maintenance, you have to usually just crawl under that very sensitive piece of instrument, and you have to wear full. You are in the clean room, so you have to protect all the instruments from any sort of disturbances, any sort of dust, because if they come to the detector, basically they start scattering light and you lose sensitivity. So this is me, and all these detectors needs to be far away from any disturbances, far away from the cities, if possible, from like railroads, from roads. But I just like to show that sometimes there are like glitches, and the detectors are protected very, very well. This card, what is this card? So the story was that there were some security guards like driving around using Google, using some roads, and then they are driving, and all of a sudden there's a hit under. The Google was basically not updated with like the changes because nobody was using these roads. So yeah, that's how they crashed. So be careful with Google. The LIGO survived. LIGO survived. Yeah, it's a very, very big concrete wall around And yeah, it has to be protected. The vacuum, these tubes are the most, I would say, if they are broken and the light and the air goes inside all these tubes, the experiment will be over. So this is the most, I would say, like sensitive piece of equipment that needs to be protected. So that's why we need to have like this gigantic infrastructure. There's also more stories, but let me go to time. So from the beginning of the observing run of advanced detectors, we detected the binary black holes during the first observing run. We detected binary neutron stars with the second observing run. Then during the third observing run, we increased even more the sensitivity, and we detected so-called intermediate mass black holes, which are black holes above 100 solar masses. Then we had pandemic, so it was like a pretty long break. Now we are in the fourth observing run, so we are basically at the end of the run. It will be over literally a month from now, 2 years long in total, with some breaks in between because of some hardware failure or some potential harmful like failures. Like one of the breaks, just to let you know, happened because one valve in the chambers was uncertain. Like people didn't know if it will break or not, and that's if it will break, the air would go inside. So they stopped the experiment. They fixed it, and it happened in Louisiana. They said, "Oh, no, we have to fix it before the hurricanes come and make potential damage." So we are like through breaks, but finally the run is getting over. So I will talk about the news from this run just in a second. But let me mention that the sensitivity of the detectors was going up to 180 megaparsecs for searching for binary neutron stars. These are our standard sources to measure the sensitivity, how far we can detect binary neutron stars. And then Virgo was stable at around like 55 megaparsecs. KAGRA detector, the Japanese detector, their goal is to reach 10 megaparsec. They almost got it. At the moment, I think the record is like 7.5 megaparsec. And they observed very, very briefly just to join the network. They also have like several like different problems. They have like one earthquake, the second earthquake, then the laser failure. So the nature was not too kind to them in Japan. Let me also say that in Germany we have like small GEO600 detector of like 600 meters. In the future, we will have LIGO India, and the construction is already underway. And I don't know, not by O5, but after O5, after the next observing run, we'll have the next detector. We should have already the next detector at least operating. And then in Australia, there was a project called NEMO, but we don't know if it will go off. But they also have plans to potentially have another detector that will be complementing the network. So fingers crossed.
And there's distance in light years, how much?
In light years?
Yes.
I usually just like multiply by 3. So it's if this is 180, like 200, so it's like 600 million years. Yeah, 500, 600 million years away from us. And in terms of like redshift, this is like it's like small 0.1, like small redshift as well. But yeah, the furthest possible event that we have detected was basically halfway throughout the universe. So for binary black holes, we see stuff like much further. Okay, so the observing ground is still ongoing, but the O4A data, so it is split into O4A, O4B, and O4C. And the first part of the data is already released. We have 128 gravitational waves. During O4B, we have detected like over 100. I mean like gravitational wave candidates. We are still analyzing the data. 100 over 100 candidates, and then the current O4C has around like 60 gravitational waves. And you can get a lot of information on the LIGO website. At the moment, we have 18 papers published on the discoveries, detections, on the upper limits, all sorts of stuff. The main paper is basically the catalog of gravitational waves that contains information about all these 128 events. And I was involved directly with some of the detections plus the search the upper limits on a supernova that happened like fairly nearby. Okay, so the first event that is of a great interest is GW231123. So 2023, November of 2023, and this is a binary black hole that ended up with a black hole of over 200 solar masses. The estimates are very uncertain. Here you have the waveform. It basically doesn't look really like an spiral where you have like inspiring phase and then merger. It's basically the end, the merger and the ring down of the final black hole. So there's a lot of uncertainty. The signal is very strong, of signal to noise ratio of like over 20. So this is a very confident gravitational wave detection. But the properties are puzzling people. And one of the nice things is that black holes, like bells, they ring, and you have the main ring ring down of if you have a bell, you have the main tone of this ringing, and then you have like overtones, you have like higher tones, and similar with black holes, that you have like the main frequency of this ringing down of a black hole, and then higher harmonics to that. And these higher harmonics are much weaker, but with this event we are able to detect one of the higher harmonics, which is great. Then I have put it here. Then GW230814, so 14th of August 2023. This is an event that was detected only with one detector. So all of practically most of the events are detected in two detectors simultaneously, but this one happened to be just in one detector. But what's remarkable is that signal to noise ratio is super high, 42, and what is another remarkable thing. So yeah, you can see a very like the inspired phase that is low, and then you see the final black hole, and within here we were able to find a different harmonic, so-called 440. So this is great that with two events we already can observe how precisely how the final black holes are ringing down, and there's plethora of different studies to test general relativity and basically constraint theories. And this is what is happening now.
Can I ask questions?
Mhm.
So it's 440. So what are these numbers?
So if you decompose gravitational wave in spherical harmonics, similar like in quantum mechanics, you have the number L and M, and then it's basically the dominant mode is 2 to 0. This is quadrupole emission. I should have like maybe like a custom slice about that, but like the dominant ringing is 2 to 0. L and M is equal to 2. N is like overtorn. So yeah, if you take your gravitational waves and yeah, you do you basically add this additional components. Yeah, the dominant is 2 to 0, and then all these like other extra pieces.
So this last, so this is these tensors, so if I'm, yes, so.
Yeah, that's right. That's right.
So the 0 is like from 0 to 2, so what is the range?
L is going from 2 to infinity,
Okay.
N is going from minus L to L,
And
and then N is from 0 to infinity. Mm-hmm. Yeah.
Okay.
Yeah. So that's like another story of yeah, how to interpret them deeper. But yeah, like the bottom line is that finally with this with in this current observing run, we are able to detect these higher harmonics. Okay, the next event is W250114, so 14th of January this year, and this is a monster of signal to noise ratio of 80, and this is a very similar to the one that is that was detected 10 years ago in GW150914. So here is like a nice comparison between our original events that yeah, you can see what they show here is basically you have plenty of still plenty of noise, but for this event that happened this year, we have it says so strong about the noise that the noise is really like way smaller, and this is like a we call it vanilla by BBA, vanilla by the vanilla black hole, so like nothing really special. However, because signal to noise ratio was so strong, we were able to precisely test the Hawking area theorem, which basically states that the area of if you have two merging black holes, the area of a merged black hole is basically higher. So it cannot be if you add the area of first and second black hole, it has to be smaller than the area of the final black hole. So this is what was tested with this event, thanks to this super high signal to noise ratio. And then the final interesting event is GW230529. So it happened right at the beginning of the run, actually during even before the run started, when we started the data tuning the detector, it's like, oh, here we go, like something like super interesting. And what's fun about that is that it is a very light binary black hole in so-called a lower mass gap. Lower mass gap is a theoretized gap in mass between 3 and 5 solar masses. When astronomical observation don't really see any much of the stars or like black holes, and there are like theories trying to explain it, but it's not like really clear. It's possible that it just basically astronomers don't see them. LIGO-Virgo already observed like 3 events, and this one is especially particularly interesting. If you take the mass of the first component, it basically lies beautifully in the mass gap, and then the second mass, yeah, the estimate is a bit less precise, but it's basically also laying somewhere like a little bit lower than the mass gap. So this is a very interesting result, showing that the rate of mergers of neutron stars and black holes might be higher than we actually expected. So for the observers, is a great news because if there's more of them, we'll be able to provide astronomers more candidates, and they can hopefully observe some of them in real time. Okay, and What's next? So we detected a few very interesting gravitational waves. What next? Here I call all these next discoveries like a special astrophysical sources. So those that haven't yet been detected, but they will teach us a lot about the universe. So we can have new gravitational wave source populations, and for the compact binaries, all the binaries that we have detected come from circular orbits. So yeah, binaries circularize and then merge, but we haven't detected yet any binary from eccentric orbit, meaning that two black holes that are basically caught gravitationally, they caught and then they merge. So they're going basically on eccentric orbit for a very brief moment of time, and it's uncertain how often it happened. You need to have a galaxy that is really dense to have these encounters, and you cannot observe that just by regular astronomical mean with electromagnetic light, but hopefully in gravitational waves we'll have some detections saying within like 10 years. Like there are some candidates that like people are debating, are they eccentric, are they not, and hopefully we'll have a confident detection someday. Then we have like hyperbolic encounters, like head-on collision of two black holes, some extreme mass ratio. The highest we found was like 1 to 10. So maybe like someday it will be like a very small neutron star with like a gigantic 100 solar mass black hole. Then people are searching for the subsolar masses, yeah, like there are some candidates, but there's nothing conclusive. Then I just marked the last binaries. So it is estimated that within 1,000 detections, and we already have like a few hundred. So in the next observing run in 05, we'll have like 1,000 pretty confidently. And then within 1,000, 2,000, there should be two events that are coming from the same source. So basically, you have one, say, that is originally like in electromagnetic lensing. You have one that is basically coming straight, and the second image that is basically bent. Its path is bent by a galaxy or a cluster of galaxy that arrives later, and it can be, say, within. There are like different types, from like mini lensing, like milliseconds. So you can have even to gravitational waves that are overlapping, to like months or years when you have to like wait until the image arrives. So that's like 2-hour bets. Then for the gravitational wave burst, something that is not a compact binary. We have core collapse supernovae, neutron star glitches. I just like to put some more like cosmic strings. And I will talk a lot in the second part of my presentation about supernovae. Then by neutron stars, we are pretty sure that in the next observing round we will have another binary neutron star that will be so strong that we'll be able to detect light. And for like new phenomena, pre-merger harmonics, higher harmonics, and the post-merger higher harmonics. We already detected two confidently, and hopefully we'll be like detecting more and more of these higher harmonics more precisely, and it will allow us to much more precisely test general relativity. So these are our 10 years, and I'm working just like the last piece of this part. I'm working with so-called model independent searches. So the most typical method that is used is a template-based searches. So you take general relativity, you calculate the waveform that you are searching for, the so-called template, and basically match it with the data. And if your prediction is good, then you have a detection. If not, no detection. So it's very, very sensitive to this. This method is very sensitive to the model that you are using. And the problem is that if you don't know exactly what you are searching for, like you don't know what the universe is made of, then you can miss some of the gravitational waves. And this is exactly what happened with the very first detection that we discovered 10 years ago, GW150914, that people were searching, saying like, yeah, these heavy black holes, they are very rare. And in order to like limit the computation, they said, oh, let's search up to 15 solar masses black holes. So like up to 15 solar masses, 15 solar masses. But what happens? The universe produces more binary black holes than some astrophysicists predict. By the way, the Warsaw group in the astronomical department, they correctly predicted that we'll find like some like such a similar event, something that is like 30 solar mass. So from the search perspective, the modeling method don't care about like what model we use. Whatever is above the noise average noise of the detector, we keep it as a gravitational wave candidate, and this is what happened here. That yeah, we have our energetic method, model independent, and it was the only pipeline, the only algorithm that discovered gravitational waves, because it was fast, the detector, people said like, gosh, like now, why? And then they basically took to the detectors, they locked it so nobody touches it, and then they were running for the next like days in order to accumulate the background. Okay, how often such a detector can create such a signal? And luckily, it was so strong that it was like so evident this must be gravitational wave. Okay, but also we have detected the intermediate mass black hole. So I just said at the beginning, something above 100 solar masses, and recently something that is like even heavier, above like 200 solar masses. Okay, so let me go to the second part of the talk, and switching gear. So I was talking about O4 and what may happen in the future, in the like near future. But now, what? Yeah, the universe is unpredictable, and stars explode and explode in our galaxy, and it's super rare. And these are, and then if you have a supernova star exploding in our galaxy within this century, it will be one of the most interesting events. And if it happens that we can see it on the sky, even during the day, if it happens, like every astronomer will be basically staying there. And we will get calls from everybody in LIGO, like, hey, have you detected gravitational waves? So yeah, like we have to get prepared. So how does it work? If we have a star, the star is burning this fuel from hydrogen to helium up to heavier elements, oxygen, silicon, and then iron. And the heavier elements basically go to the center. And if this iron core exceeds 1.4 solar masses, then basically gravity takes over and basically collapses the core. And that's the beginning of violent processes that drives the explosion. Basically, protons and electrons meet with protons, creating neutrons and neutrinos that are escaping. 99% of this explosion energy escapes with neutrinos. However, we still don't understand, we still don't know how the stars explode, what is the explosion mechanism, or maybe there are a few mechanisms. So there's a lot of work, and these are one of the most difficult astrophysical objects to model. So when it can be detected? If we have at the moment we are doing basically constraints and if we scan the frequency range and say like how, if you remember the generational gravitational waves, the more asymmetry, the stronger gravitational wave emission. So if the collapsed core rotates really fast, you might have something like this cigar shape objects that are emitting strong gravitational waves. Then you can have such cigars rotating predicted with a little bit more sophisticated numerical simulations, and then you have more realistic explosions that such asymmetries are rather weak. And if you look at the most typical, the most realistic, the most aggregate numbers in terms of gravitational wave energy, they're emitting like 10 to minus 9, 10 to minus 9 of solar mass. So like take a sun and then like 10 to minus 9, just a small piece of it is converted to gravitational waves. For a comparison, binary black holes, they're basically out somewhere here, like they're out even this scale. It's basically 1, 3, 5 solar masses emitting gravitational waves when they merge. The most efficient generators of gravitational waves. So supernovae are like way lower here, like much many less energy emitted. And if we take the current observing run 04, we are able to place the constraint somewhere here, still like orders of magnitude away. But this way we are learning how to make the detection. So realistically, we need a galactic supernova to make a detection. Then what happened? So there's a lot of groups that are modeling these sources, and there's us, the gravitational wave astronomers, and just this summer, and some of you who are here now were actually at the symposium. We had a meeting between gravitational wave observers and the modelers. Like all of them came here to Warsaw, basically from all over the place. A lot of people came from the US, people from Asia, people from Australia. Geographically, it was close, so people from Europe. And we were discussing what we should do in order to, if we have a galactic core collapse supernova, what should we do to actually extract physics, as much physics as possible from this one in a lifetime event. So there was we had plenty of discussions. We had people talking about the theory, our side of gravitational waves. Because neutrinos are important, we've also had some discussion about the neutrinos, electromagnetic spectrum, and then what we can expect, how we can improve the situation within like 10 years. If anybody is interested, we also have all of the talks on YouTube. We are at the moment working on the proceedings and the white paper. So proceedings are for students. These are short, usually like short papers that are basically summaries from conferences. So this is what what is happening now. We working on these papers and on these proceedings, and we'll be writing a white paper that will basically summarize the interactions and like how to move forward. Just to give you an example, if a gravitational wave happens, we have the data, but we cannot say anything for months, while like astronomers, modelers, neutrino observers, everybody will be like putting pressure, like, hey, give us the data now, like we need it. It's fainting. So that's one of the discussions, like how to interact how to make it how to make this collaboration efficient. And a quick summary of what we are doing here in Warsaw. So, like our contribution to the symposium. If you take all the papers on gravitational wave from core club supernovae, I separate them into like a theory oriented, so like, oh yeah, we have the simulation, and this is what we see. From data analysis oriented papers, which is basically, oh, we have that model, how we can work with the noise, how we can work with the data in order to make to detect some emission process. And then there's some data analysis parameter estimation papers. So basically, we took some of the methods and we try to combine them into one analysis that provides really fast information of what we actually see. So you can actually see that the field of gravitational waves from core club supernova is still fairly young. The number will be like increasing, and we are uncertain when a core club supernova in Milky Way happens, but it will happen. It will be gigantic. So just a flashback on what we are doing. I had like 4 intern students and total of like 10 projects with people from here, from the astronomical department. We took this is how the emission from core club supernova likely looks. Here is the collapse of the core. We have so-called from convection, and we're trying to understand like how we can detect it. A lot of work came here, so-called high frequency feature. Basically, when the core collapses, it basically is cooling off, and then it's shrinking. The density is getting stronger, and the gravitational wave emission is basically getting higher. So this is the strongest emission that we predict to see, and we had like 2 people working on that, and then the lower frequency emission when you have like a shock that is basically sloshing into that collapsed core. Then we're trying to distinguish whether it's possible to see from what part of the star this part is coming from this part of the star is coming from, what is like the total energy of the emission, can we do anything like based on gravitational waves, how the supernova was oriented. We had like some project. If you are interested, you can actually listen to the sound of gravitational waves from core club supernova, and also like some other readings as well in this webpage. And then like some other how to mathematically describe these gravitational waves. There are like different formats, and then we try to decipher that. So that was our contribution, like 10 projects from people. And then some of the lessons that we have learned during the symposium is how to combine the gravitational wave, neutrino, and electromagnetic waves in terms of making a detection, how to do parameter estimation with all these like three multi-messengers. So we have a detection, and then how to say what was happening inside, like what is the size of the proton neutron star, what is the rotation rate, what are the other rotational properties. So it's something that we are discussing. How to make that interaction between the communities. So as I said, if you have the data, we cannot say anything for months. And yeah, like a lot of people are curious, but that's how it works at the moment. We try to improve it. Then there is some consensus of, as I showed in the previous slide how the gravitational waves look. There is some consensus on how it looks, but there's still a lot of stuff that has to be done to really understand, like, yeah, this is the schema that we are really searching for. Many uncertainties about the structure of the progenitors. So, like, if you have an initial star, this needs to be a lot of improvement. It's like initial condition to your simulation, and it's something that needs to be improved. Some hidden assumptions, like transport of these neutrinos. You have a huge amount of neutrinos, and people are treating them like in a different way. They model them in a different way, and how to evolve technically and organizationally in order to maximize the science. There is also like plenty of other lessons, but I will not bother. I will skip them. So let me go to the summary. So the fourth observing round will end in a month. So we have 128 gravitational waves that are confident, and then 164 that are gravitational wave candidates. 4 of them that were already published test different areas. We have like 2 that allows detecting higher harmonics. One that confidently tested Hawking area theorem, and some astrophysically very interesting events. And for Core Club Supernovae, we are preparing for the next Galactic Core Club Supernova, and it can happen anytime. And we want to be prepared. And we hosted this first symposium here in this department. And this is the first meeting of 2 communities, gravitational wave and external communities. And hopefully it will be one of the meetings of a series. And also additionally, if this coordination goes really well, it will be an example for like testing GR, for astronomers, for any other communities that will be interacting with gravitational wave astronomers. So we are working on it. So that's all what I wanted to say today, and thank you very much.
Thanks for the question.
I have to do this stuff after.
I have a good question.
Yes.
So you mentioned detecting these higher harmonics. So do you expect all higher harmonics in the spectrum, or what is the theoretical prediction for it? Is it maybe all, or?
Yeah, theoretically they're all.
Sorry?
Theoretically they're all present, but they're so weak that they're under the nose, so they're not detectable. They are like a order of magnitude weaker than the main emission. But yeah, like according to GR, they are there. They are there in the data.
This measurement that detected them would be like very precise that was detectable from the noise.
Yeah, and it's basically based on GR. So we already have better models for the waveforms from general relativity, and like they're like you cannot. I say we have general relativity and we have models, so it's not possible to just like plug any parameters to GR and take whatever you want. One simulation can take like a month even, like a precise simulation. And you have to make this a lot of approximations. And that's why even if you have a GR, very precise, beautiful theory, you still have to like model based on GR. So there are like different models and different algorithms that do the analysis that they agree that, oh, okay, we see the same thing. If there will be some ambiguity, and maybe it's not so strong, or maybe something else is showing up. Yeah, like according to general relativity, all of the harmonics are there. Say like at different amplitudes, at different levels, but we need to have such a strong event, such a high signal to noise ratio, in order to start like they start appearing. It's like if you have a noise and you start seeing the gravitational wave, it's like, yeah, do you really believe it? It is like close to the level. So now we have very strong events, and then we start probing these little pieces that are like this additional little pieces, additional phenomena like this higher harmonics.
And the second question would be, so as far as I understood, the most events that we detected are black hole mergers or maybe neutron stars mergers and things like this. So what would be a spectrum of different events? For instance, would it be any different, like transition to cosmic string, for instance?
People like cosmic strings, but it's yeah.
Because
I don't know too much about them, but but what is actually, yeah, aside the binaries, corpulent supernovae are the strongest emitters, because you have fairly dense matter, and you have yeah, like all this like violent motion inside. So like people predict that, yeah, maybe aside binaries, we'll see gravitational wave from supernova. That's why there was like so much attention to that. It's like, yeah, we are bored of this binaries. Like, what next? And it's like, yeah, maybe supernova. But
okay, so I'm curious how the spectrum would be. How does it look like? Because in this mergers, you usually see the ring down that is the most prominent, and how can like an estimation out of curiosity from this?
yes. So actually, I'll apply to that. So binary black holes, they have like this tubing structure. So like the merger and then ring down. Then the frequency is like up to like 300 hertz. So up to 300 hertz, we are searching for binaries. But for the corpulent supernova, it's much longer. It's like this is like an example. So it's half a second, and the spectrum is like up to 2000 hertz. So if you plot this guy over here, it will be just like tiny some. This is like 500. So it should be like somewhere here, like a small dot. So
they are much more wide.
yeah, they are much longer. It's like half a second, 1 second, and the frequency spectrum is much higher, like 2 kilohertz, like up to 2 kilohertz. So it's also much more challenging. This stuff is just basically just pops out from the noise. This stuff, yeah, it's very slowly going up above the noise. So it's like it's very challenging to even search for them.
Okay. Yeah.
But also just to add other sources than binaries. People are searching for the pulsars. So if you have a rotating pulsar, is there enough asymmetry in order to have gravitational waves that are continuous and they're detectable? Yeah, at the moment they are still doing the upper limits. Maybe in 05 we'll have some confident detection of these continuous waves from a pulsar.
You mentioned these harmonics and these numbers over 0, I think it was. You mentioned it was kind of analogous to like quantum mechanics in the momentum. And my question is, could you have somehow a quantum model for these rotational waves?
There are attempts, and there are actually people who are, I don't want to lie, but it's like taking the Schrödinger equation and then like calculating the waveforms. It's using they try to use the formalism of quantum mechanics in order to like model that, but still these are yeah, like some interesting approaches, but observationally what is like most important is to take general relativity. Yeah, like yeah, like we can have like all these approximations, all these attempts, but at the end of the day, it's GR that governs governs the calculation. So yeah, people try, but for the detection, general relativity is the theory. Yes, classical. Yeah, I can also say that if you will not be seeing these higher harmonics, something will be wrong with general relativity. Like some theories of gravity, they predict that there are no higher harmonics. So then if we like have strong signals, like yeah, we should have seen these higher harmonics, but we don't see them, then maybe like other theories of gravity are correct. But so far, GR rules.
Another question.
What I would like to ask about this Hawking area law. You said that the final area is bigger than area of Earth and black hole, but maybe there is some summation law of areas of these two black holes. It's not only bigger, but some. And you
Yeah. So taking this, oh, not this way. Yeah. So this is like fractional difference. So the final minus the initial. So if they would be equal, it would be like 0. So yeah, they're like you sum them and it's higher. It's not it's this is actually the measurement. When you have the spiral, you actually it's not like you add the area of the first black hole plus the area of the second black hole, and it's the sum. Because during the process, there's a lot of gravitational waves that are emitted. So the final area is smaller than just a sum. If you have like two masses, then the final mass is different than the sum of the two. So similarly, I would say for the area here that even if you add the areas of two black holes, it's smaller. The final area is smaller than the sum of the two, just because a lot of gravitational waves basically were emitted. So final black hole is smaller of like few solar masses than the mass, the sum of two components. This is
how long can you wait for supernova?
it's a gamble.
But on averages.
It's like 1 per century, but the last one was like 300-400 years ago.
Now you should have all.
Well, they might happen on the other side of the galaxy. So yeah, it's 1 per century. But then because it happened there, it's like thousands of years before it reached Earth. So yeah, like it's they say it's a very rare event, but a golden event. If we have it, then we don't know how the stars explode, and the gravitational wave will allow us to directly probe what is happening inside. Yeah, it is yeah. If it happens, it's a big thing. If it doesn't happen, yeah, it's like we are still waiting. But eventually it will happen in this century, in the next century. Eventually it must happen because the stars explode. Yeah, I think like Kepler saw 2. He was lucky guy. He saw like 2 orbital supernovae during his lifetime, and they were like on the sky. Yeah. So hopefully, yeah, we can also encounter that.
Yes, thank
Yeah.
you very much.